the next thing I want to talk about is e to the x, what we often call the natural exponential function. And this is kind of a more confusing function because e is a very special number, which is a little bit hard to explain the importance of without some calculus. But basically, it's the most important exponential function. It's very critical to mathematics, science, and it often models how things grow naturally, a very natural progression of the base, which is why we call it natural exponential function. And when we wrap up this chapter, and we talk about it in class this week, we're going to look at some applications, and a lot of times real world exponential growth is modeled by e to the x, just due to the usefulness of the base. But anyways, what is e is kind of the next question. And if you're not really sure, almost all scientific calculators should have e somewhere on it. And if you notice right above the division sign and you look real closely at your calculator, you can see there's an e there. And if you just go second division, basically e is a very special irrational number which is stored in the calculator. It's approximately 2.718 or 2.72, depending on your rounding preference. And it's a very, it's not an unknown, it's not a variable, it's a constant value. So, like in math, sometimes we use letters like A, B, X, C to represent constant values, or to represent variables unknowns. But, often we also use letters to represent numbers we know, and that's the important thing about e. It is a very specific number. It's always the same number. Well, actually, technically, in other subjects, e can mean different things, but in any mathematical situation, the lowercase e is always referring to this particular number. Often we call it Euler's number, Euler's constant, based on some history. Actually, let me pull up my slides real quick, and I'll talk a little bit about the history of the natural exponential function, because we'll look at its graph and its things as well. But basically, e is a number much like the number pi. Pi is a very popular number in our culture because 3.14159, it's a number which is infinitely long, has no repetition, no repeating digit, and it's called an irrational number. And we've actually dealt with a lot of irrational numbers so far in our class when it comes to polynomials. Like right with the quadratic formula, sometimes we get irrational zeros like 1 plus the square root of 3 from the quadratic formula. But pi is kind of like a number like that, has to do with circles and stuff like that. But the reason why I bring up pi is because e is very similar. It's a very specific number, and it exists. It's kind of hard to explain why it exists, but it's a very important mathematical constant. Pi is so important because it has to do with circles. It always is the ratio between the circle with, well, I'll draw a quick little sketch here. Let's say we were to take a circle with a diameter of exactly 1 foot. So like imagine, sorry, very sloppy, I'm not very good at drawing with my mouse. Imagine you, you see a car and we're looking at the tires of the car. Let's just say it has 12-inch rims, very, about a foot. They'd be really small rims, but some people like to have those little tiny wheels on their cars. I don't really know why, but it's a thing. But anyways, imagining a wheel like that, basically, if it has a diameter of exactly 1 foot, the circumference, basically the distance around that circle, would be exactly what pi is. It's 3.14159. Again, it's not a terminating decimal. It's an infinitely long string of non-zero, non-repeating digits with no discernible pattern. The only reason the numbers, and the question arises, why is this such a weird number? And how would I ever figure it out? Well, you can't ever figure out the whole number because it's literally an infinite digit. But the reason it is what it is just because some people attribute it to God or creation or things like that, but basically it's a natural constant. If we have a straight line in a circle, there is not a direct mathematical ratio. It's not like 1 to 2 or 1 to 3. If we have a straight line with distance 1, pi would always be the circumference of that circle, and it basically relates straight lines to circles. And it just is what it is. There's basically, our whole mathematical system that we have invented as humans doesn't have a very good way of relating those types of numbers together. Hence why we often refer to them as irrational. They're just and the reason they were coined as irrational numbers historically is just because of their complexity, and they're hard to understand. And E is very similar. It's less. It doesn't have anything to do with circles, but instead has to do with progression of natural growth, and we'll kind of talk about that in a minute longer. But it's very relevant to finance and natural exponential growth. We also refer to these numbers pi and E. They actually have a special name called. They're often referred to as transcendental numbers, and basically because they transcend algebra, and this kind of relates back to our polynomial theorems and our talk about factorization, but we've seen irrational numbers arise from polynomials like the square root of 3 or 1 minus root 5, those as being the roots to a polynomial function. And there are algebraic solutions which can arise from, say, the quadratic formula or from a polynomial equation. But numbers like pi and E, they're basically so complicated that irrational numbers, they're much like pi and E, like these two, in that and we would refer to these as non-transcendental numbers, but because they are algebraic solutions to polynomials. But they're very similar in that, if you type this in your calculator, you're going to get 1.7 blah 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 blah. It's an infinite string of non-repeating digits, and all of these types of numbers are called irrational just because they don't really fit our decimal form very well. So coming back to pi and E, these we would refer to as non-transcendental, whereas pi and E are transcendental because they transcend even algebra. They're never going to be a root to a polynomial equation, or basically they're just even more complicated than these numbers. They're not related back to simple situations, but they're very important to various things. Like pi is very important with circles, triangles, trigonometry, all that. E is very important in a lot of other aspects. And Leonhard Euler, a very famous mathematician, he standardized a lot of modern mathematical notation. He was one of the first people to use E as a representation to this very special number. It's not that he invented it, but he sort of discovered and popularized its use. And he discovered a lot of really other super important aspects of E in the field of complex analysis, which is why he's probably my favorite mathematician, if I had to pick. Anyways, let's return back to I'm getting carried away with history and random stuff once again, but let's return back to the packet and just try to finish up the talk on e to the x. But anyways, that's more than enough on what is e to the x power, the natural exponential function. But basically, let's say we wanted to evaluate in the same way and figure out domain, range, and all that stuff. Well, basically, it's not all that different than 4 to the x or 2 to the x or 3 to the x. It's just a different numerical base. And we can always use a calculator to figure it out, because the base of this is a very complicated number. And let's say we wanted to raise it to the 0 power. Well, anything to the 0 power is always 1, so that's an easy one. But e to the first power would just be equal to e itself. So that would be approximately, and again, I'm going to use the squiggly equal signs to show that that's not exactly 2.72, but approximately. And say I wanted to know what is e squared. Well, again, I would want to go to a calculator because it is such a long number. And also to mention, notice that above the ln button right here, there's also e to the x power, which is the exponential function. So e is actually in 2 spots in your calculator. It's right there, and it's right there. If you want just the number, you can use this one. If you want the exponential function e to the x, you can use that one above the ln. And we'll talk about ln shortly as well. But e to the second power is going to be approximately 7.39. And I could continue. What about e cubed? That is going to be approximately 20. And if I were to graph some of these points, I could get an idea of what this looks like. But it's going to look very similar to our graph of 4 to the x from the previous video. So notice it has the same exact y-intercept right there at 1. E to the 1 is going to be about 2.7, somewhere about there. E squared is going to be about 7.39. And e cubed is going to be up at about 20. So very similar shape to that of 4 to the x. But since the base is smaller, it's a little bit less steep. It's a little bit more gradual. And you can kind of think about the base as sort of like a factor in the steepness of the growth factor. And that's really what the base is all about. Now, if we were to do e to the minus 1, that would be 1 over e or 1 over e squared. Again, we could fill those out with a calculator. 1 over e is approximately 0.37, and 1 over e squared. But basically, as I move to the left, or as x approaches minus infinity, it's going to get smaller and smaller because I'm dividing by an ever-growing value of e. 1 divided by e squared is going to be about 0.14. And, you know, say, for example, I wanted to know e to the 1/2 power. Again, that would represent the square root of e, and this would be 1 over the square root of e. Very, very complicated calculation. And just, you know, as another tangent to get on, I don't know if you've ever wondered, like, how does the calculator actually know these things? Like, did someone just program a million different things in there, or, you know, or what? But this is something that you start to uncover if you ever have to take Calc 2, second semester calculus. You'll talk a lot about what are called Taylor polynomials or Taylor expansions, Taylor series or Maclaurin series. But basically, there are ways of taking a mathematical function such as e to the x or 4 to the x, and actually expanding it into something that's much like a polynomial. Now, technically, what's different is it's not a finite polynomial like x to the 4th. It's actually an infinite polynomial. But basically, a calculator is very good at doing polynomial math. It's just a combination of multiplication, adding, subtracting. And polynomials are sort of a simpler baseline function. Exponentials are actually quite a bit more complicated, even though they seem simpler. But basically, you can actually reduce exponential functions into a bunch of polynomials, and that's one of the ways that calculators work. Basically, it grinds through all these calculations. Very interesting subject, but anyways, sorry, another tangent that's not relevant, but how do calculators work is another interesting question. Anyways, that would be about 1.65. And we can use our calculators to do a lot of heavy lifting, but, you know, in modern day, it's a lot harder to really understand why all these things work the way they do. And that is a very key component in really knowing math. But anyways, filling in the rest of the points, we would have, you know, e to the 1/2 is about 1.65 and would fit into that curvature. And e to the minus 1/2 would be about 0.61. But anyways, it has a very consistent curvature to it. Obviously, we can use a calculator to try and figure it out. But basically, e has the same sort of sketch. E to the x has the same sort of sketch as 4 to the x or 2 to the x or whatever. And one last thing to mention, I talked a little bit about this already, but one way that e is often defined in calculus textbooks as being the end behavior of the following mathematical expression. Basically, if you look at this particular function based on n, as n approaches infinity, this is basically what we can explain e to be. And like, if you take this in your calculator and you start plugging in really, really big numbers into this, like let's just say I started with 100. I would have 1 plus, actually let's start even with just 10. I would have 1 plus 1/10, or 1.1, and I'd want to raise that to the 10th power. That would give me 2.59. Okay, well, I don't know, what's the point? But let's just see, let's say we're plugging 100. What would happen next? And just explore what happens as we make n increasingly large. Notice that plugging 100 into that weird expression leaves me with about 2.70. And basically, if you keep going or you keep plugging larger and larger numbers into this would be a way to generate e, or basically as we're going, we're developing a better and better approximation to what the value of e is. Notice 2.716, it's getting further and further. And let's say I went all the way to 1 million. I did 1 plus 1 over 1 million and raised that to the 1 million power. Notice that would give me 2.718. It's getting closer and closer to that number. And basically that is one of the ways e is defined. If you're like, what is e? How do I define it mathematically? You could define it as the end behavior as n approaches infinity of this particular expression. And that's complicated, right? And if you're like, what the heck is this and why? Well, in the next video, I'm going to talk about basic finance and exponential growth functions for simple, compound, and continuously compounded interest. And we'll kind of see why this expression is relevant, and why does this whole math come into play in terms of E. Anyways, that's it for this one.